There is an irresistible allure surrounding black holes that captivates our imagination and leaves us in absolute awe. Picture yourself standing on a distant planet, gazing up at a night sky where a massive star, brighter than 1,000 suns, suddenly erupts in a blinding flash. This is the supernova, the violent death throes of a giant star, scattering its outer layers across space like cosmic fireworks exploding in slow motion over thousands of years. From the remnants, an invisible monster is born, a black hole that devours everything in its path. This fascination might stem from that dramatic origin, or perhaps from the terrifying concept that once anything, even a beam of light racing at 186,000 miles per second, crosses into a black hole, it vanishes forever, like a message dropped into an endless void with no return address. The ultimate enigma resides at the very core of these objects, a place where the familiar laws of time and space as we understand them completely break down and cease to function in any recognizable way, as if the universe itself hits a glitch in its programming. Whatever the reason for this profound intrigue, black holes, and especially the mysterious entity at their centers called the singularity, stand out as some of the most puzzling and intellectually demanding phenomena in the entire universe. Scientists have spent decades pondering their properties, running supercomputer simulations that model collapsing stars in vivid detail, showing clouds of gas swirling inward like water spiraling down a drain, accelerating to near-light speeds before disappearing. These simulations help visualize the invisible, turning abstract math into dynamic scenes of cosmic destruction and creation. For more than 100 years, humanity has inhabited a universe shaped and explained by Albert Einstein's general theory of relativity. This groundbreaking theory has successfully accounted for a vast array of cosmic events and behaviors, ranging from the origins of the universe itself in the Big Bang, an explosion from a point smaller than an atom expanding into the vast cosmos we see today, to the precise and stable orbits of planets around their stars, like Earth gracefully circling the Sun year after year without drifting away. Einstein's framework revolutionized physics, providing tools to predict gravitational waves, ripples in spacetime detected in 2015 when two black holes collided billions of light-years away, sending tremors through the fabric of reality like waves from a stone tossed into a pond. It also explains the bending of light around massive objects, as observed during a solar eclipse in 1919 when starlight curved around the Sun, confirming Einstein's predictions. Ironically, however, Einstein himself never envisioned or accepted the astronomical wonders we now know as black holes, despite the fact that their mathematical foundations were embedded in his own equations from the very beginning. Black holes are defined as regions in space where the gravitational pull is so extraordinarily intense that nothing, not even electromagnetic radiation like light, can escape once it has ventured inside a certain boundary. Imagine throwing a baseball toward the sky with all your strength. On Earth, it arcs and falls back due to gravity. Near a black hole, even if you hurled it at escape velocity faster than light, which is impossible for matter, it would curve back inward, trapped forever. Although the first direct image of a black hole, specifically the one at the center of the galaxy Messier 87, was captured only in the year 2019 using the Event Horizon Telescope, a global network of radio telescopes working in unison like a planet-sized camera, revealing a glowing orange ring of hot gas surrounding a dark shadow the size of our solar system. Evidence for their existence had been theoretically present in Einstein's equations since he first published them in 1915. Einstein, however, staunchly refused to believe in them. He considered the idea of an object capable of utterly collapsing the established laws of physics to be implausible in the natural world, much like dismissing a fairy tale monster as too outrageous for reality. To acknowledge black holes would mean accepting the presence of a singularity at their heart, a point where every known natural law grinds to a halt and becomes meaningless, akin to dividing by zero in mathematics, resulting in infinity and nonsense. This personal resistance from such a prominent figure created significant obstacles and delays in the scientific community's exploration and acceptance of black holes for many years, slowing progress like a traffic jam on the road to discovery. That changed dramatically in the year 1965 when the physicist Roger Penrose mathematically proved that, Within the framework of Einstein's equations describing the universe, singularities are not merely possible but inevitable outcomes when an enormously massive object undergoes gravitational collapse. Penrose's rigorous theorems demonstrated how matter could compress to infinite density under its own gravity, leading to these breakdown points in spacetime, illustrated through pen and paper diagrams of light rays bending inescapably inward, never to return. His pioneering work earned him the Nobel Prize in Physics in the year 2020, at the impressive age of 89, recognizing his contributions to our understanding of the universe's most extreme environments. The full acceptance of black holes by the scientific community did not, however, resolve all the mysteries surrounding them, particularly those tied to the singularity. Many questions remain about what truly happens at these points, and they challenge even the most advanced theories in physics today, including efforts to reconcile general relativity with quantum mechanics, where scientists imagine tiny vibrating strings or looping quantum foam replacing the smooth spacetime curtain. To make these abstract and complex ideas more relatable and easier to grasp, consider starting with something everyday and familiar, like the wooden table you might be sitting at right now while reading this. You can see and touch this table, and it feels solid and substantial, supporting your coffee mug without collapsing. Yet, its density is only a few grams per cubic centimeter, which is far too low to ever form a black hole under normal circumstances. On the scale relevant to black holes, this material is simply too sparse and lightweight, like trying to build a mountain out of feathers. To create one, we would need to compress the table enormously until its density reaches unimaginable levels, packing all its mass into an incredibly tiny volume smaller than a pinhead, turning your sturdy furniture into a gravitational powerhouse. The challenge lies in the fact that matter naturally resists such compression. The more you try to squeeze it, the greater the internal pressure builds up, and the stronger the resistance becomes, much like trying to crush a spring that pushes back harder with every bit of force applied, or squishing a balloon that inflates elsewhere to compensate. Overcoming this requires an event of staggering power and energy to surround and compress the table into a minuscule, ultra-dense state capable of warping spacetime into a black hole. Envision the table enveloped in a sphere of exploding dynamite 1,000 times more powerful than all human nuclear weapons combined, yet still insufficient for the task. One such cataclysmic event capable of unleashing the necessary energy is a supernova, an apocalyptic explosion on a galactic scale. This occurs when a star that is truly gigantic, with a mass at least 30 times greater than our own Sun, reaches the end of its life cycle. In a matter of mere seconds, the star detonates with blinding fury, brighter than an entire galaxy for a brief moment, ejecting its outer layers into space at speeds up to 10% of light, forming beautiful nebulae like the Crab Nebula, a glowing cloud visible through telescopes as a remnant of an explosion witnessed by Chinese astronomers in 1054. What remains of the core then collapses inward under gravity's relentless grip, condensing into a black hole in less than a heartbeat, releasing energy equivalent to the output of billions of suns, illuminating the cosmos and seeding the universe with heavy elements essential for planets and life, including the iron in your blood. Classification of black holes. Stellar black holes. The supernova process described above is primarily responsible for creating the most common type, known as stellar black holes. Recent astronomical calculations and observations suggest that within our Milky Way galaxy alone, there could be anywhere from 10 million to 1 billion of these stellar black holes scattered throughout its vast expanse, remnants of long-dead massive stars, lurking invisibly like ghosts in the galactic neighborhood, occasionally revealed when they pull material from a companion star, creating X-ray bursts detectable by satellites. Supermassive black holes. In addition to stellar varieties, there exist supermassive black holes, which astronomers believe lurk at the centers of most large galaxies, including our own Milky Way. These behemoths can have masses ranging from millions to billions of times that of the Sun, and their formation mechanisms are still a topic of active research, possibly involving the merger of smaller black holes in galactic collisions that look like two swirling pinwheels fusing into one, or direct collapse of enormous gas clouds in the early universe, compressing under self-gravity like a snowball rolling downhill growing larger. In fact, Roger Penrose shared his Nobel Prize with astronomers Andrea Ghez and Reinhard Genzel, who provided compelling evidence for a supermassive black hole at the heart of our galaxy. They observed stars orbiting an invisible object in the region known as Sagittarius A, moving at extraordinarily high speeds up to millions of miles per hour, whipping around in tight ellipses like race cars on a track, only explainable by the gravitational influence of something with about 4 million times the Sun's mass compressed into a space smaller than our solar system. To comprehend why this points to a black hole, imagine massive celestial bodies and the fabric of space-time as a flexible rubber sheet stretched taut. Objects like Earth and the Moon have mass, and Earth's mass curves the space-time around it, creating the gravitational dip that keeps the Moon in orbit, much like a marble rolling around a bowl, circling indefinitely unless disturbed. Our Sun does the same on a larger scale for the planets in our solar system, with Mercury hugging close in its shallow dent while distant Neptune orbits the outer rim. A star destined to become a black hole, however, starts with a mass tens, hundreds, or even billions of times greater than the Sun. Upon collapse, this immense mass squeezes into an infinitesimally small volume, producing a curvature in space-time so profound and steep that anything approaching too closely falls inexorably inward, unable to climb back out, similar to a pit so deep and narrow that escape velocity exceeds the speed of light, like rolling a ball into a bottomless funnel where it spirals faster and faster until vanishing at the center. Event horizon. This inescapable boundary is termed the event horizon. It forms an invisible spherical shell around the black hole, demarcating the point of no return and separating the interior from the rest of the observable universe, like a one-way membrane in a science fiction portal. Once an object or particle crosses this threshold, it is effectively lost to the outside world, disconnected from all external communication or influence. Observers from afar would see time slow down dramatically for anything nearing the horizon due to gravitational time dilation, with the falling object appearing to freeze in place eternally, reddening and fading like a video pausing on the last frame, though from the object's perspective, it crosses smoothly without noticing the boundary, continuing its plunge in what feels like normal time. We remain uncertain about the ultimate fate of matter that passes beyond this point, but everything inside is compelled to journey toward the singularity at the black hole's center, pulled by gravity that grows ever stronger, stretching objects in a process called spaghettification, where a falling astronaut would be elongated like taffy, feet pulled harder than head until torn apart long before reaching the center. Singularity. It is precisely at the singularity where space-time as we comprehend it utterly ceases to exist. Here, matter is theorized to achieve infinite density within a volume approaching zero, a state that defies intuition and calculation, like cramming the entire mass of the Sun into a thimble or the Earth into a marble. Einstein's equations predict this breakdown, but they fail to describe what occurs, as no current physical law, including quantum gravity theories still under development, can adequately apply, evoking images of a cosmic dead end where clocks stop ticking and rulers lose meaning. This is why many physicists regard black holes, and the singularity in particular, as the greatest unsolved puzzle in theoretical physics. It forces us to confront the limits of our knowledge, hinting that a more complete theory uniting relativity and quantum mechanics is needed to resolve these paradoxes, potentially revealing new insights into the fundamental nature of reality, perhaps involving wormholes or information preservation in holographic forms. Building on the intricate wonders of the universe, let us now explore another equally enigmatic state of matter, plasma. In the vast expanse of space, particles behave according to rules quite different from those we experience daily on Earth, dancing to electromagnetic tunes rather than simple collisions. The cosmos beyond our planet is almost entirely filled with this mysterious form of matter, which is the least understood on our world yet plays crucial roles in celestial displays, like the Sun's fiery surface boiling with plasma storms, and even impacts human space exploration efforts, where solar plasma bursts can fry satellite electronics like a microwave overheating popcorn. This is plasma, recognized as the fourth state of matter following solids, liquids, and gases, achieved when you heat a gas so intensely that atoms lose control of their electrons. The nature of plasma. Plasma consists of particles that have become ionized, meaning they have absorbed sufficient energy to strip electrons away from their atomic nuclei, as happens in a lightning bolt cracking through the air, ionizing it into a glowing plasma channel. As a result, plasma no longer comprises intact neutral atoms but instead forms a dynamic mixture of positively charged ions and free-floating electrons, akin to a subatomic soup where charged components intermingle freely, buzzing with activity like bees in a hive. Unlike ordinary gases, which are poor conductors and drift aimlessly, plasma conducts electricity with remarkable efficiency, lighting up in neon signs where electric current excites the plasma to glow in vibrant colors. This property allows it to flow along invisible pathways shaped by electromagnetic fields permeating space, responding dramatically to magnetic forces and enabling complex interactions on cosmic scales, such as plasma jets shooting from the sun's poles like garden hoses spraying water. The dominance of plasma. Though plasma is rare on Earth, appearing naturally in phenomena like lightning strikes that briefly turn air into plasma hotter than the sun's surface, or artificially in neon lights, television screens, and experimental fusion reactors aiming to harness star-like energy, it dominates the observable universe, constituting 99.99% of its visible matter. This includes the Sun, a gigantic ball of plasma 1 million times the volume of Earth, churning with convection currents that drive sunspots and eruptions, other stars twinkling as plasma furnaces, and the diffuse material filling interstellar and intergalactic space. Far from being a vacuum, the void between planets and stars contains a thin, weak plasma interspersed with electromagnetic fields generated by celestial bodies such as the Sun and Earth, carrying solar wind particles across the solar system like a gentle breeze bearing seeds. Magnetic reconnect ion. In regions where plasma interacts intensely with electromagnetic fields, an explosive phenomenon called magnetic reconnect ion can occur. This happens when magnetic field lines continually shift and become tangled, like rubber bands twisting around each other, then suddenly snap and realign with a burst, releasing tremendous stored energy, accelerating surrounding plasma particles to extreme velocities, akin to a slingshot flinging a stone. Magnetic reconnect ion drives solar storms and flares on the Sun, where reconnecting fields launch coronal mass ejections, billion-ton clouds of plasma hurtling toward Earth at millions of miles per hour, potentially disrupting communications like a global blackout. It generates shock waves near supernova explosions, rippling through space like tsunami waves after an undersea quake, and twists plasma violently in the accretion disks around black holes, heating material to billions of degrees and producing jets that pierce galaxies like laser beams. Closer to home, it plays a key role in transferring energy around Earth. For instance, when reconnect ion takes place on the night side of our planet between solar and terrestrial magnetic fields, it funnels plasma particles toward the poles, energizing the atmosphere to produce the Aurora borealis and Aurora australis, those breathtaking curtains of light dancing across polar skies in greens, purples, and reds, shimmering like ethereal veils woven by invisible hands. Modern plasma research. The space immediately surrounding Earth offers the ideal laboratory for studying magnetic reconnect ion in detail, where NASA's satellites orbit through the action like detectives at a crime scene. The National Aeronautics and Space Administration, or NASA, pursues this through the magnetospheric multiscale mission, which deploys 4 identical spacecraft flying in a pyramid formation to measure magnetic fields and particles in 3 dimensions at speeds 100 times faster than previous missions, capturing reconnect ion events in real time like high-speed cameras filming an explosion frame by frame. This unprecedented resolution uncovers fine-scale details of reconnect ion events and the intricate behavior of plasma, revealing electron-scale processes previously hidden. Other NASA endeavors, including the Parker Solar Probe diving close to the Sun's surface, skimming through its corona where plasma temperatures reach millions of degrees yet particles remain sparse like a hot oven with little inside, the Artemis program exploring the Moon and beyond with instruments sampling lunar plasma environments, and the long-lived Voyager spacecraft venturing into interstellar space, now bathing in the plasma of the galactic medium after 40 years of travel, continue to investigate plasma throughout the solar system, from the Sun's corona to the heliosphere's boundaries where solar plasma meets interstellar winds. Through these efforts, NASA persistently unravels plasma's secrets, paving the way for safer space travel by forecasting space weather, better predictions of events that can affect satellites and power grids on Earth like preparing for a hurricane, and deeper comprehension of the universe's fundamental processes, ultimately helping humanity reach for the stars.